but apparently active has some other ideas. So there were some interesting things about aromaticity that came up over the weekend that I'd like to touch on. One of your classmates contacted me about the homework and said, I think one of our learning objectives is to learn how to do resonance structures with aromatic compounds. And I was thinking back to what we covered in class, and now I don't think that resonance is one thing that we're focusing on a lot. But then I went through the homework with them, and sure enough, like it does feel like you're doing a lot of resonance. It looks like you're doing a lot of electron arrow pushing to find the aromatic resonance form. So I wanted to talk to you guys about some aromatic features. Pi electrons outside of the ring don't count towards the aromatic system. Because we said that an aromatic compound is cyclic, planar, fully conjugated, and then has to have some pi electron count equaling 4n plus 2. So here's a really common compound called quinoline. It's a diketone. Do you think this compound would be aromatic, anti-aromatic, or non-aromatic? I heard anti. What'd you say?
I don't think it's aromatic right now because it's not. That's what I was confused on. It's not
Well, yeah, that's not
continuous. Like,
well, yeah, it is.
Is it cyclic?
Yes.
There are parts that come off of the cycle. That's true, but we looked at structures like this, and we said that's aromatic. You know, and we could just as easily say that's aromatic. We're looking at a portion at least that is cyclic. Is it planar? Usually planar and fully conjugated go hand in hand, because if you are sp2 hybridized, then you are trigonal planar. And this molecule is trigonal planar at every single atom in the ring, so it must be a planar structure. And then is it fully conjugated? Well, there are sp2 carbons all the way around. So it matches all of our rules for aromatic and anti-aromatic. What about the pi electron count? Well, if I only count the electrons that are within the ring, which means I wouldn't be counting these carbonyl pi electrons, then I'd have an anti-aromatic system. I'd have 4 pi electrons. But there's actually something a bit odd about saying that these 4 electrons get to touch all 6 of the carbon atoms, but I don't get to count the electrons that are outside of them. It creates for kind of it doesn't work to both count those atoms, those carbons as being conjugated, and to count to not count their pi electrons. So this compound might seem like it's anti-aromatic, but it actually does something really interesting where it breaks its own conjugation in order to avoid being anti-aromatic. So all 4 of these atoms are conjugated with each other. That creates this little conjugated system. And then all 4 of these atoms are conjugated with each other, but there's a split in the conjugation. Would you predict that? No. Am I asking you to predict that? No. Okay, so then we had this other question that showed up in your homework. What happens when this compound becomes protonated? And the question was show the aromatic resonance form after this gets protonated. Okay, there are 2 ways that this could protonate. There are 2 oxygen atoms that could become protonated. I could protonate the one on the top, or I could protonate the one on the bottom. But we know that not all positions are equally as basic. One of those things that contributes is resonance. If resonance can help delocalize a positive charge, then it can stabilize the conjugate acid that forms. there's no resonance in this structure down here. Especially none that cooperates with this oxygen. For instance, if I want to get rid of that positive charge, I need to give that oxygen more electron density. But that oxygen already has a full octet. It can't accept more electron density without breaking a bond. So there is no resonance on this form. But what about this form? Well, I want to get electron density to the oxygen, and I can do that by breaking a pi bond. That would leave me with a positive charge now on my carbon. Does that indicate the aromatic form? So according to the homework, it does, and I think that we can now rationalize why it does. Is it cyclic? Yes. Is it planar? Yes. Is it fully conjugated? Well, we run into one of those heteroatom hybridization questions, which is, I have to consider this oxygen. The oxygen looks like it's in an sp3 bonding environment. If it's sp3, it's not fully conjugated, it's not aromatic. If it's sp2, then it is fully conjugated, and the pi electron count is 2, 4, 6 aromatic. So oxygen is sp2 hybridized because it allows for aromaticity. But does this look like your aromatic bonding pattern? Not really. So the way that we can get there is then move one of these pi bonds and have oxygen's lone pair also form a pi bond. Well, one thing that active gets really hung up on is show all lone pairs. If you put any lone pairs on the carbons, it's wrong. If you put more than one lone pair on the oxygen, it's wrong. If you had any charge on this other oxygen, it's wrong. So they can be really picky, but apparently they were happy with this. So that's good, at least. So I want you guys to recognize this as an aromatic bonding pattern. And there are some other characteristic aromatic bonding patterns as well. One of them is similar to our furane or imidazole ring, a 5-membered ring with a lone pair. Whether nitrogen holds that lone pair, or oxygen holds that lone pair, or even if carbon holds that lone pair. I'm just putting Y there because Y could be a negatively charged carbon, an NH group, or an oxygen group. It actually doesn't need to be H, it could be R. So that's a characteristic bonding pattern. You've got that 5-membered ring, and one of the atoms has a lone pair, potentially a charge. If it's, no, it's not pyridine.
No, but it's like the same structure, right?
Pyridine is the nitrogen 6-membered ring. And we've got that similar situation going on here, correct?
Yeah.
You could have a positively charged oxygen, you could have a nitrogen, or you could have a carbon in that 6-membered ring. That's an aromatic structure. So we get these familiar bonding patterns.
I think in the book too, like the reason why I got that structure, I think in the book has a structure similar to that, but it was a 5-member ring, I think, with nitrogen or something like that, and then
Which is called imidazole.
yeah, and then they took that positive charge on the carbon. It was weird. That's why we ended up in that structure, you know.
So you went from this, and the textbook showed you this.
No.
You went from this.
No. That's what I kind of copied to be able to get to that.
Okay.
When I was adding, because it was a reaction with water or something like that.
Yeah.
And I said, well, the difference here is that I have an extra oxygen and a ketone. So obviously I'm going to have an OH at the end. I have to have an OH at the end. But then the carbon must have
It works, but actually let's go back to a conversation we had in our first week on resonance forms. Which of these is a more major contributor to the molecule? The resonance form that has minimum charges, they share the same charge, and maximum octet. Maximum octets. Here I've got a carbocation. Here I have no carbocation. Every atom has its octet on the right. One carbon is missing its octet on the left. But I can see how you would get there. Actually, another common example of aromatics forming in reactions is to take something like cycloheptatriene with this sort of halogen on top of it. And if I do some sort of solvation reaction, this compound very quickly breaks off its iodine. Why?
You mix those
Sorry?
to become aromatic.
Right. It goes through SN1 far easier than any other compound because that carbocation is an aromatic carbocation. Forms very easily. If anything, it would be hard to actually finish substitution and put something else on it. Then we had another conversation that came up today, which was some other resources that showed the delocalization of the heteroatom lone pairs. So we did some analysis last week. We said that this oxygen atom, although it might appear that it's sp3 hybridized based on its bonding pattern, if it were sp2, the molecule would be aromatic. So there's an energetic preference for oxygen being sp2. And then we said one of these lone pairs on oxygen is localized. It's never going to leave the oxygen. And the other lone pair is delocalized, which means it doesn't belong to oxygen. It's a part of the aromatic system. And if it's a part of the aromatic system, which atom is it on? All of them. It's a part of the aromatic system. And we can show that by these resonance forms. One of these resonance forms pushes the double bond from position 1 to position 3, from position 3 to position 4, from position 4 to position 2, excuse me. And then from position 2 to position 4. Moves it all the way around the ring. Delocalized. Are any of them necessarily, I'm sorry, I kept forgetting to put my positive charge on O. Are any of them necessarily a major resonance contributor? This one is the one that has minimum charges. Is there any benefit from looking at those other resonance forms? Yes. It tells us that oxygen is not the nucleophile you might think it would be. We see oxygen in water, oxygen in alcohols, oxygens in ethers act as nucleophiles, but this oxygen, not nucleophilic. So there is something beneficial to learn from that. And second, it tells me that all of these other carbons in my ring are actually more nucleophilic than you might expect. They have this partial negative charge due to the resonance. Now, we're not going to spend so much time on heterocyclic aromatic reactions, but this idea of delocalized charge indicating reactivity is something we're going to dive into in section 16. Now, I want to give you guys another perspective on this. A lot of you have some biology inclination, probably better biology training than myself, so feel free to step in here if I say something you don't agree with. You know what these are called?
Oh, these are your
The DNA.
Nucleotides. Those are nucleotides, right?
The nucleotides. I always forget the difference between nucleotide and nucleoside.
Oh, yeah, that's.
This is the nucleotide, and when it's connected to a larger, like the sugar and stuff, it's a nucleoside. Other people call them the nitrogen bases. Is that true?
So this is just the nitrogen base, but when it's connected to the other things, that's when it becomes a nucleotide.
Okay. So our nitrogen bases here are fairly stable structures. And that stability may be the result of aromaticity. And if you look, one of these DNA bases actually perfectly demonstrates aromatic structure. If you look at adenine, we've got this 5-membered ring on the left and a 6-membered ring on the right. It is complicated to draw, huh? Boom. Almost. So a couple of things to point out. I see some pyridinyl hybridized or pyridinyl bonded nitrogens. The nitrogens that bond just like pyridine. And we know that pyridine is an aromatic compound. What do we know about the lone pair on pyridine? Is it localized or delocalized? This is a localized lone pair, which means it does not count towards aromaticity. Here's a localized lone pair. How do I know that? Because it's bonded just like pyridine. Here's a localized lone pair. Here's a localized lone pair. Bonded just like pyridine.
Can you just do it out of patterns, or is there?
Yeah, you've got this 6-membered ring with alternating 3 double bonds. 6-membered ring, alternating 3 double bonds. 6-membered ring, alternating 3 double bonds. That's another part of the aromatic bonding character.
I think there's an amine, extra amine.
Did I? Oh, you're right. Thank you. Do you know what? I think I was looking at guanine when I copied down that amine. Good catch. Attention to detail is super important. So these lone pairs, localized to their nitrogens, not a part of the aromatic system. But what is a part of the aromatic system? Pi bond, pi bond, pi bond, pi bond, and we call this the imidazolian lone pair because it resembles the lone pair on imidazole. We said that imidazole is an aromatic compound. So the lone pair on imidazole, is it localized or delocalized? It's delocalized to make the compound aromatic. So you've got 2 types of lone pairs that show up on nitrogen. Localized lone pairs, similar to the ones in pyridine, and delocalized lone pairs, similar to the one on imidazole. So I've got this 5-membered ring with 2 double bonds and that lone pair. I've got this 6-membered ring with alternating 3 double bonds. The heteroatoms, they don't need to make things more complex. They look just like situations we've seen. We're just seeing them in a new context. So adenine, aromatic compound or anti-aromatic? Or maybe I could say this. Does adenine have aromatic character or does it have anti-aromatic character?
Aromatic.
It has aromatic character. It does not have anti-aromatic character. All right, now let's look at something like thymine. Now, with thymine, it comes back to this situation we talked about before where we can't count pi electrons that are not within the ring towards the aromatic pi electron count since we only consider the ring. It has to be cyclic, which means we don't count these pi electrons. But if we don't count those pi electrons, it's more challenging for us to also count the carbon atoms in the conjugation. And one of our rules is that it has to be fully conjugated. So there is a resonance form that I can draw that highlights the aromatic character more easily. I take the carbonyl pi electrons out away from the carbons. So now my carbons will be able to be counted with full conjugation. Then with the nitrogens next to them, I take their delocalized lone pairs, because remember, these nitrogens are bonded more like imidazole. They're not bonded like pyridine. And now what do I get? I've got this carbon-carbon double bond. Now I've got a carbon-nitrogen double bond. And down here, I've got a new carbon-nitrogen double bond. What else do you guys notice about this structure? Sam, you might have a good perspective on this.
Like referring to aromaticity?
Not necessarily. Just about a unique character that this resonance structure has.
Oh, don't the oxygens are got nucleophiles, so it makes it easy to make the backbone.
That's true. That's true. I was going to say it's got a lot of charges, right? It's got 2 sets of positive and 2 sets of negatives, which means, is this a major resonance contributor? It's hard to say, because the bonding pattern really enforces aromaticity, but it results in a bunch of charges. And then you've got this other great connection, which is the whole point of these molecules is to hydrogen bond with one another across the backbone. What's going to happen to nitrogen's ability to share its hydrogen through hydrogen bonding? Increases. That oxygen now has a positive. It's going to be pulling on its electrons more strongly. It's going to hydrogen bond better. Oxygens now have a full negative. They are able to hydrogen bond a lot better. So these compounds may not look aromatic at their first resonance form, but we can draw a resonance form that highlights their aromatic character. And in drawing that, we also reinforce their hydrogen bonding. So there is something to be said about maybe a resonance form that highlights aromatic character is more important than a resonance form that minimizes charge. This is not a learning objective that any textbook gets into. It's just an interesting perspective that I like to apply towards our DNA. Caesar, you got a question?
Yeah, is that what the homework was trying to do when we were talking about showing the dipole?
Yep.
Okay.
So the last question that we can cover on this one, and then I think we'll be good to move. We had this 3-membered ring bonded to this 5-membered ring, correct? And they shared a double bond. Now, would you look at that molecule and predict a dipole? Where's the electronegative atom? Where's the less electronegative atom? You wouldn't. So the homework told you there is a dipole. And I'll tell you the dipole points this way. This side of the molecule is more negative, and this side of the molecule is more positive. Electrons are not distributed the way that you'd like. And again, I can see how the homework kind of reinforced your learning objective is resonance structures. It's not. Your homework is identifying common aromatic bonding patterns. Well, one of our bonding patterns was this 5-membered ring when carbon has a negative charge. What about a 3-membered ring? Was there a common bonding pattern there that made it aromatic?
There's one, there was like a double bond and then a positive.
What if it had a negative charge?
And it was like, there was a radical or something.
Yeah, it made it anti-aromatic. And the MO theory shows us that anti-aromatic compounds have unpaired electrons. So I could take this pi bond in the middle and I could give it just to the carbon on the left and take it away from the carbon on the right. Or I could take that pi bond in the middle and I could take it away from the carbon on the left and give it to the carbon on the right. In this first structure, I've actually created two regions of my molecule that have anti-aromatic character. So double the anti-aromatic character. But then in this version, I've created two regions that have aromatic character. So I could rewrite this. And I'm going to draw it big because I don't want my little circle to be confusing. Circle with a positive charge, circle with a negative charge. To indicate there is a dipole in this molecule that you might not expect there to be. I guess this gets into another interesting way that questions can be asked in this chapter, which is, I normally lean back on, does this compound have aromatic character, or does this compound have anti-aromatic character, or does this have non-aromatic character only? Because some compounds, I think we can agree, can have some non-aromatic character. Like, look at this this NH2 group, that's non-aromatic character. That doesn't contribute to aromaticity. I think rarely you're ever going to have a question where a molecule has both aromatic and anti-aromatic character, because it's just kind of hard to do, you know? If I gave you a structure like this, there are two separate rings. One is anti-aromatic, one is aromatic. So this would be a compound that has both types of character. But if I fuse those rings, and I guess I'll kind of show their double bond along the fused edge. Does that compound have aromatic character, anti-aromatic character, or both?
Aromatic.
It doesn't have aromatic character, even though it looks like it's got that six-membered ring. The problem is that now it's not just a six-membered ring. It's bicyclic, fused. So I have to consider all 8 atoms. I can't consider just 6 or just 4. I have to consider all. Because I count 10 electrons, because I count 8 electrons, anti-aromatic. Even though it looks like this little portion. Okay, a couple of questions. We'll start with Sam.
Okay, and that was the rule where it's like if there's like 2 rings,
Yep.
and they're both fully conjugated, then you have to count.
You've got to count all of them. You can't cherry pick. We did talk about that towards the end of last week, correct? We said, here's some weird instances. Like the other ring doesn't look conjugated at all, don't count any. The other ring is partially conjugated. It's got 1 pi bond, don't count it. Or the other ring is fully conjugated, you've got to count everything.
When it's not conjugated, we don't count the small one without the other one.
Correct. Well, let's take an example. Let's change this double bond such that this atom has 2 hydrogens, so the ring is not fully conjugated with the 6-membered, and then this has a negative charge, which means it has a lone pair. The same number of pi electrons are here. And actually, this lone pair is conjugated to the ring. It's stabilized by being in a p orbital, so it can push its electrons into the ring. But this carbon is not fully conjugated. So when I count aromaticity, I only count pi electrons that are in the fully conjugated ring. I don't count electrons that are outside of my fully conjugated ring. And I don't count electrons that are outside of a fully conjugated ring. I promise I'm not trying to trick, but it is a challenging subject.
Then what would you qualify that compound?
This one,
The one you said, yeah.
now aromatic.
Okay.
This one, anti-aromatic.
Is the first one aromatic or the aromatic character?
Yeah, that's what
Yeah, this one here, I would say, has aromatic character and has anti-aromatic character. This has only aromatic character. This has only anti-aromatic character. I don't think you'll see a problem like this. This is an odd example. It's one that I created so that I could highlight when do you count all of the rings? When does it impact everything? All right. Now we gotta do some work here. Okay. Section 16 takes us from exploring aromatic compounds to performing reactions with aromatic compounds. Now, today we have an hour left. I want to talk to you about some of the goals, the learning objectives we're trying to walk away with. We're going to look at two primary classes of reactions. One where the ring acts as a nucleophile and one where the ring acts as an electrophile. When the ring acts as a nucleophile, we call it electrophilic aromatic substitution. When it acts as an electrophile, we call it nucleophilic aromatic substitution. So this is one of our objectives. Pay attention to these terms. One of your goals will be to be able to distinguish them and know what reagents go to each and what characteristics go to each. We're going to look at predicting electron arrow pushing mechanisms. When I say predicting, there is kind of a caveat on there. I'm usually looking for a plausible mechanism. That means that electrons are flowing in proper ways. It also means that you show all major resonance forms of any conjugated intermediate. It also means that certain atoms need to play certain roles. And if you choose to have other atoms playing different roles, it stops being plausible. Maybe not impossible, but just not plausible. So this is another big objective of ours, is to be able to do this. In addition to distinguishing EAS from NAS, we're going to be talking a lot about activating and directing effects. That is, if it's not just benzene on a ring, if there are substituents on that ring, those substituents impact the character of benzene. Similar to what we saw with the oxygen in fluorine, it impacts the character of the rest of the ring. So we'll be looking at distinguishing how those substituents activate rings and how those substituents play a directing effect. And all of this really accumulates into some multi-step synthesis as well. We're going to be learning a lot of reagents. We're going to be learning when to provide which reagent. So you guys have some written work for this section. It's one mechanism you have to show, and it's one multi-step synthesis you have to show. And I encourage you, after today's class, to take a stab at the mechanism, and then after probably tomorrow's class to try and take a stab at the synthesis and submit it Thursday so that I can grade it Friday and give you feedback. Because what comes after Friday? The unit test. We have a unit test this weekend. Opens Friday, closes Monday night. And guess what you'll have to do on the short answer part? Show a mechanism, do a synthesis. So I want you to have those skills down. I want to be able to give you feedback. And I might have time to do that in class here, but homework is a great way for me to just give you feedback on what you've got. Okay. So first, I want to give a generic aromatic substitution. I'm going to show our aromatic ring here. And the goal is to put something onto it. Now, aromatic substitutions are not quite like the substitution reactions we learned in OChem 1. This is not SN1, and it's not SN2. If anything, they're sometimes called SNAR, but that's a specific class of reactions. But all aromatic substitution reactions actually follow two steps. They follow an addition step, and this could either result in a negative charge forming within the ring, or it can result from a positive charge forming in the ring. So I just want you guys to recognize there are two different ways to add. Do you guys remember maybe a definition of what addition reaction means? An addition reaction it won't take away a hydrogen. Actually, this substitution, I think you're noticing there's a hydrogen going away. But in addition, you'll notice there's no atoms lost.
Is the pi bond you break in order to
A pi bond is consumed, exactly. And we can see that a pi bond is consumed. Well, actually, you can't because I did my little circle. But if I drew these incorrectly, then you can see a pi bond is consumed. It's consumed in different ways, would you agree? In this case, the pi bond is consumed. The electrons go to one carbon. But in this way, the pi bond is consumed. The electrons have been lost by one of the carbons. Different ways. Then the second step is elimination. So this aromatic substitution is actually a two-step process, minimum. Addition followed by elimination. Before we get too into these reaction types, I want to give you the major classes we'll be looking at. Electrophilic aromatic substitution is often referred to as EAS. But I want to remind you that you should actually read this name backwards. Substitution of an aromatic ring with an electrophile. That's how it's meant to be read. What is the nature of the aromatic ring? The ring acts as the ring is being substituted with an electrophile, so the ring must be a nucleophile. That's why I said oops, because I put an nucleophile. Does the ring have electrons that it can donate? Yes, it has pi electrons. It can take one of those pi electrons and it can donate it to an electrophile. If it acts as a nucleophile, what charge will it take on within the ring? Positive. It's losing electrons. And then we're also going to look at things that increase the nucleophilic character. We're going to call these electron donating groups. EDGs. And my red is dying, so I'm going to finish describing this. Electron donating groups improve EAS reactivity. So we will be looking at electron donating groups after we get some onto our structure, all right? Oh, I didn't actually give you a generic reaction. Yeah, actually the only thing I think you have the idea with the generic reaction, so I'm gonna put this. That's kind of our most important intermediate. Takes the positive charge. E here is talking about the electrophile. The ring has donated to the electrophile. Then we have our generic nucleophilic aromatic substitution. Now there are two ways that this can be named. One of them is NAS, the other is SNAR. When you talk about SN1, SN2, we are saying first order nucleophilic substitution. Second order nucleophilic substitution. When we say SNAR, we're saying aromatic nucleophilic substitution. The ring is we are substituting the ring with a nucleophile. So how does the ring behave? The ring is an electrophile. What does that mean about the intermediate? It will have a negative charge. The ring has accepted electrons. So if I give you the example here, actually the best intermediate is going to have something a little bit surprising. Where this nucleophile attaches to, we're going to put X. And X here, for us, will be a halogen. Which is not to say it can't be other things, but that's the leaving group that we'll be using this semester. X is a halogen. If the ring needs to accept electrons, then it would actually benefit from having substituents on it that pull electrons away. That will create more positive character in the ring, make it a better electrophile. These we call electron withdrawing groups. EWGs. And these improve NAS reactivity. I think linguistically I need to make a clarification. Compared to what? They improve reactivity relative to
Base reaction.
benzene. If it's just benzene, it has nothing else going on, that's going to be a base reaction. That's our control. But as soon as you start putting electron donating groups or electron withdrawing groups onto the structure, now you've got changes to reactivity. I think actually it would be more meaningful for us first to go through and make a table of these electron donating groups and electron withdrawing groups. There's a couple of ways that I could do this. I could put a benzene for each group, and that can kind of show us how it behaves on each group, how it connects to the ring. Or I could give like one ring with all the groups, or I can just list the groups out. Do you know what I think I'll do? I'm gonna give one example of a group on a ring, and then beneath that I'll give the rest of the groups. Electron donating groups often have lone pairs. So if I look at this nitrogen group, and this nitrogen group has two R groups coming off of it, maybe those are hydrogens, maybe those are methyl, maybe that's a whole other ring. But this nitrogen has a lone pair. How does it impact the ring? Well, it makes the ring a better nucleophile. It gives the ring more electron density that the ring can then share. How does it do that? It takes its lone pair, donates it to the ring, pushes out a lone pair within the ring. Would you agree that this creates a negative charge on the ring? And what balances that negative charge?
Conjugation.
A positive charge on the nitrogen. We say that this electron donating group is conjugated to the ring. Is that the only position that that negative charge appears? Mm-mm. We can look at the next resonance form where the negative charge is now directly opposite the electron donating group. How would you describe that using benzene terminology? The negative charge is blank to the electron donating group. Para, P. Mm-hmm. First, we saw the negative charge ortho, then we saw the negative charge para. And lastly, there is one other resonance form where it shows up on this last ortho position. So I'm actually just going to give us an abbreviation here. Electron donating group gives me nucleophilic character at these positions, ortho and para, to the electron donating group. All right, now there are some donating groups on here that are fairly weak. I've actually got these organized by increasing electron donating effect. You'll notice at the bottom that I've got alkyl groups like methyl. Yeah, and I think I drew a neopentyl, and I wanted to draw tert-butyl. Does a methyl group have a lone pair? No. Does a tert-butyl group have a lone pair? No. So these are not electron donating groups that have lone pairs. They're not actually conjugating electrons to the ring. But they do have an inductive effect into the ring. And you can see that the smaller the group, the smaller the inductive effect. The larger the group, the more electron donating it is, the larger the inductive effect. Can you talk to me about why OH and OR have differences in electron donation?
Because of the hydrogen instead of oxygen, they're already correlated.
Do you think the relationship here between OH and OR is similar to the relationship here between CH3 and CCH3? It's a smaller group, less induction. Larger group, more induction. So now we can see the same thing for NH2 and NR2. Larger group, more electron density, more induction towards the ring. Can you talk to me about this? Oxygen versus nitrogen. Why is nitrogen a stronger electron donor?
Because it doesn't want the electrons as much as oxygen.
It doesn't want its electrons as much as oxygen. What term do we give that?
Electronegativity.
Right. Nitrogen is less electronegative. So nitrogen has a lone pair, happy to share. Oxygen has a lone pair, can't share, just might not. So nitrogen is actually a better electron donor. All right, electron withdrawing groups often have pi bonds connected directly next to the ring. Let me show you one with benzaldehyde. Now we know that benzaldehyde has a resonance form where the CO double bond goes to oxygen. Does that impact the ring? Not yet. But if this carbon takes a positive charge, then it can borrow electrons from the ring. You'll notice now that I've got a negatively charged oxygen and my ring is conjugated to the carbonyl. You can see the pi electrons bridging from a ring carbon to the carbonyl carbon. What is that position relative to the benzaldehyde? Where is that positive charge found? Not meta. Yeah, here's the ring bonding to benzaldehyde. Here's its ortho position. And is this the only spot? No. That conjugation continues, and it gives me a position here, para to that group as well. Now if I sum this all up, and I think we can agree there is another resonance form at the other ortho position. But if we sum this all up, here's what we get. Electron withdrawing groups put a partial positive on the ring at positions ortho and para to itself. I want you guys to think about what kind of character this emphasizes. Negative character emphasizes nucleophilic behavior. It weakens electrophilic behavior of the ring. The ring can be both. Partial positives increases electrophilic character of the ring. It's now more willing to accept electrons there. It decreases nucleophilic character of the ring. So these two types of groups, they have two very different effects. All right, I'm not sure that I can get these in the correct order. I'm going to do my best. Nitro groups, and I'm actually going to show you the nitro group does have a pi bond, but we often abbreviate it as NO2. If you need to show the nitro group being responsible for pulling electrons out, you'll have to expand it to really draw its structure. Sulfonyl groups, SO3H, and again, we abbreviate this a lot, but it does have a pi bond when you draw it all the way out. It's got 2. Carbonyls. That carbonyl could be an aldehyde, a ketone, an ester, carboxylic acid. Truly, any type of carbonyl will have this effect. And lastly, the cyano group. Probably the most unique one because the cyano group has a triple bond. Okay, there is a class of atoms, class of groups in here that are not listed. Does anything stand out to you guys? Think. What type of atom have you not seen listed up there? Name some of the atoms you do see listed up there. Halogens are not there. Got oxygens, nitrogens, sulfurs, but there's no halogens. Am I suggesting that halogens are not electron donating groups? And neither are they electron withdrawing groups? Am I suggesting that halogens have no effect on how aromatic rings behave? I'm not. Halogens, though, play the middle ground. So we're going to see some interesting behavior when it comes to halogens. They don't follow all of the characteristics of electron donating groups, but they can be predicted to donate their electrons. And they don't follow all of the behavior of electron withdrawing groups, but they do have the ability to pull electron density away from a ring. So they share characteristics of both of these sets of groups, and we're going to look at them in that way. All right. Do you guys need a break? Have I worn you down yet? Because if you don't take it now, it's just going to be forever. You won't get one. Okay, good. Love to hear it. Let's start to look at some of these reactions, shall we? I want to hear from you guys. I've got 2 ways of putting this up on the board. One way is to give you the reaction, so you get to see the reagents and what it produces. and then later come back and give you the mechanisms. Or I can give you the reaction, then the mechanism, then move on to the next reaction, show the mechanism. You want to see all the reactions in one spot and the mechanisms in one spot? Are the rest of you indifferent? Or you have a preference? Well, here's what I would encourage you then. I'll put all of the reactions up, and if you'd like to see those mechanisms directly next to the reaction, just put it in there. Leave some space and then come back in and fill it in. And like, really leave some space. Okay, we're gonna start with our EAS reactions. And I'm actually going to start with the reactions that we'll need to know the mechanisms for, and I'll end with the reactions that I'm not going to ask you to know the mechanisms. I'm not asking you to only learn some of them because some are harder and some are easier. I'm really finding the more common ones, the ones that I think are more beneficial for us. All right, let's start with bromination. Here's benzene. Here is bromobenzene. In order to accomplish this electrophilic aromatic substitution, I will need elemental bromine and a catalyst of iron 3 bromide. Two, chlorination. If I start with benzene and add chlorine with the catalyst aluminum chloride, then I can substitute a hydrogen with a chlorine. Did you guys know that I could write everything over the arrow on the left-hand side of the arrow? Writing it over the arrow just condenses the space a little bit more, and it draws your attention to the primary organic substrate. All the rest of this are just what I might add to the thing I want to react with. Momi. Does it matter that I put bromine and chlorine at the same position on the ring? Did it matter which position I put those halogens on? No, just preference for drawing, right? Good. So far, so good? Great. 3. This is called Friedel-Crafts alkylation. Who are Friedel and Crafts? Don't know, never met them. Crafts is not the craft of mac and cheese. And if I were to name this reaction, it wouldn't have their names in it. I would have just named this reaction alkylation, EAS alkylation. Now, what this does is it adds an alkyl group, an R group. I'm going to give us a specific example, one that highlights some interesting character about this, okay? That is 1-chloropropane, or N-propyl chloride, with the catalyst aluminum chloride. Where was that catalyst last used? In our chlorination. So there's a correlation here between I've got a chlorine group and I'm using the same catalyst. You might predict that I'm going to substitute the hydrogen and the chlorine, and I'm going to create that carbon-carbon bond, and I'll make propyl benzene. But I don't. The synthesized product is isopropyl benzene. Can you tell me what's happened in that reaction? There's a lot of right answers here.
It connected at like the middle carbon.
It didn't substitute on the primary carbon. It substituted at the secondary carbon. Did something happen to that secondary carbon during the reaction? Or has nothing changed to that secondary carbon? It's just bonded to the ring. Let's check.
About hydrogen.
2 hydrogens here, 1 hydrogen here. That's a hydride shift. That's a structural rearrangement. What type of intermediates give us structural rearrangements? So this has a carbocation intermediate. Are there ways to get N-propyl benzene? Yes, just not by alkylation. 4. Do you know what? I think I spelled Friedel wrong. So I'll give you both spellings in case you want to know which way is right.
Question about the last one.
Yes, sir.
Calculation. Is it always was it aluminum chloride as the catalyst, or just for that specific?
No, that's, at least in the reactions that I set up, we'll stay consistent with alkyl halides and aluminum trichloride.
Doesn't matter what alcohol halide we're using, like if we're using bromine in that case.
Do you know what? I would accept swapping it for bromine. In fact, I've seen textbooks say it doesn't matter the nature of the halogen or the catalyst, that those can be interconverted. For instance, you could run Cl2 with FeBr3, and you can run Br2 with AlCl3. I've seen that listed. I don't know what the benefit would be if you get into a laboratory setting. And I think I've seen something similar where you could have an alkyl chloride with FeBr3. I would accept having an alkyl bromide with FeBr3. You show me the thought process. I'm sure that you'd be able to figure out what reagents actually need to be used by the time you get into the lab. Does that seem fair? But you will see a consistency. Alkylation will always be an alkyl chloride for me. What about acylation? EAS acylation. What's being added? An acyl group. And what's an acyl group? Give me an example or a definition. COOH is an acyl group. Specifically, what acyl group are you mentioning there? A carboxylic acid. So, more broadly then, what are all acyl groups? Carbonyls. CO double bond, that's our acyl group. So, I want to take a similar structure. This is called propanoyl chloride. It's an acid chloride. It's not a carboxylic acid, but it's the chloride version of a carboxylic acid. We'll use the same catalyst, AlCl3. This is going to add an acyl group, and I want you guys to pay attention. I've got the same number of carbons, and my chlorine is connected at the same position. This does go through a positively charged intermediate, but there is no rearrangement. That carbonyl group does not allow for rearrangements. So this is actually a benefit to us. What if I want to get a straight carbon chain connected to my benzene? I can't do that using alkylation, but I could get a straight carbon chain through acylation, and then I could make it an alkane chain What reaction could I use to make it an alkane chain?
So potassium
Potassium permanganate
for 24 hours.
will take an alkane chain and turn it into a carboxylic acid.
H2 PDC.
Close. Do you know what? There are reactions with aromatic rings and hydrogenation, like H2PDC, H2 with nickel. I'm actually not going to show you guys any hydrogenation of alkenes this semester. Again, not impossible. I just feel like it's not one of the targets for me. It does start with H2, but then it's got a lot of other things, and then it ends with H2. It's not a lot of other things. H2, N, NH2, which is hydrazine, and we call that the Wolff-Kishner reduction. So there's a way to take carbonyl to straight alkane, and that would actually synthetically allow me to avoid this issue. All right, these are the reactions that you may need to show a mechanism for. And I will say that the mechanisms for 1 and 2 are very similar, and the mechanisms for 3 and 4 are very similar. So if you get familiar with these two sets of reactions, you'll get familiar with the mechanisms. You don't have to learn a bunch of different stuff. Number 5 is the nitration reaction. Nitration adds a nitro group, NO2. And it does this by reacting nitric acid with sulfuric acid. It is the battle of the acids. It's a really interesting mechanism. I'm not going to go through it with you guys because I think it just takes up more time than is necessary. But the sulfuric acid protonates nitric acid, which is already an acid, which kicks off a molecule of water. That gives me the NO2 positive group that the ring can then attack. Sulfuric acid here, catalyst. AlCl3, catalyst. FeBr3, catalyst. I realized I forgot putting catalyst after I got to FeBr3, but these are all catalysts. All right, our last EAS reaction is sulfonation. Man. What is this going to add?
Sulfide.
Not a sulfide or sulfoxide. Close. This will add a sulfonyl group. SO3H. There's a really complicated stuff between sulfide, sulfoxide, sulfonyl, mainly the number of oxygens. And the reagents here, this is SO3 and H2SO4. What role do you suspect sulfuric acid plays here? Catalyst. Now this is an interesting reaction in that the reagents really don't lose anything. They don't create any byproducts. In bromination, there is a byproduct. FeBr3 is a catalyst, so that should be regenerated. There's an equivalence of Br that goes missing and something else. The what?
The HBr.
Catalyst. The hydrogen that the bromine replaces. So there's a byproduct in this reaction of HBr. There's a byproduct in this reaction of HCl. It accounts for the second chlorine, and it accounts for the hydrogen that got swapped. There's a byproduct in this reaction. More HCl. Byproduct in this reaction. HCl. byproduct in this reaction. No, not quite.
Water.
Water. So there is an O and H from nitric acid, and then the H from the aromatic ring. This reaction loses a molecule of water. What about my last one? I said none already. Okay, we notice that the hydrogen in each of these reactions goes missing. The hydrogen that gets substituted ends up in the byproduct. Where does the hydrogen here go?
At the end of the.
Yeah, it gets added to the end of the SO3. I'm adding SO3 and I create SO3H. So the H never actually leaves the molecule, it just gets replaced, moved into a different spot. Sometimes you will see this listed as fuming sulfuric acid. I'm not exactly sure on the definition there of fuming, but my understanding is that if you've got concentrated nitric acid, H2SO4, it can create a gas phase mixture of H2O and SO3, which together is H2SO4. So that's how you can generate some of the SO3 in there. Okay, I do want to point out a couple of things. Which of our electron donating and electron withdrawing groups have we learned how to place onto a benzene ring?
What?
Which of our electron donating and electron withdrawing groups have we learned how to place onto a benzene ring? No, not quite. Halogens, which actually were not either electron donating or electron withdrawing, but kind of both.
The nitro.
We've added the nitro group, the sulfonyl group. We added the carbonyl group, the acyl group. Did nitro? Did the halogens?
That's it.
The alkyl groups. So we have not yet learned how to place oxygen groups, nitrogen groups, or the cyano group onto there. So what type of reaction do you think we'll see that in? These are all of your EAS reactions, by the way. 6 EAS reactions. How will we ever get a molecule that has OR or NR2?
Doing these reactions and then doing an EDG reaction. Maybe
NAS. So if these groups cannot be placed onto a molecule using EAS, then they must be placed onto a molecule using NAS. So either I will give you a starting material that has this group, or you'll use NAS to put these groups on. This is really confusing. There's a lot of back and forth. We're saying that these groups improve the reactivity of EAS, but to get them onto the ring, added via NAS. It's kind of a backwards game, right? And these groups, the ones that improve NAS, these groups were added via EAS. There's a lot of back and forth, so I'm going to be trying to get you in the right mind frame. How do you think about it so that you don't get the directions jumbled? All right, I'm going to erase that list now. Are you guys okay with that? Great. And by the way, we haven't yet seen the electron donating or the electron withdrawing effect of these molecules or of these groups. All we've seen is if I start with benzene, how do I even get that on there so that it can now change the reactivity of the benzene ring? But to wrap up today, we're going to look at mechanisms. And we will not look at the mechanism for nitration or sulfonation because it's just too dang hard. No, not at all. Because it's, in my opinion, it's so much more prevalent for these reactions to be done that I would like you to understand how they run. Most of what happens in nitration and sulfonation is like acid-base chemistry. But there's some real interesting organic chemistry that happens here. Okay, bromination. Now, what I am going to do in this mechanism is keep everything up throughout the entire mechanism. If you're not interested in showing each little thing, then you can kind of have it come and go as it needs to. That does mean, though, that I'm going to show the benzene ring even before it starts reacting. The first step of this reaction is actually the activation of the catalyst. Benzene will sit there. Br and Br will react with FeBr3. One of the bromines donates its lone pair, creates a complex with iron. You can abbreviate this as FeBr3, but I had a student last semester who said, I understood the reactivity a bit better when I saw all of those other bromines drawn out. It gave me an awareness of the steric environment, the spatial environment. And then I'd like you guys to recognize the charges. What charge is on that middle bromine? Why is it positive? Sorry? Yeah, it's just donated electrons, so now it has less electrons for itself. It has 2 bonds. How often do you see bromine with 2 bonds? Rarely. Bromines often only have 1. You got a follow-up, Caesar?
Kind of. So I thought this would be, isn't this like an ionic reaction, right?
This here, this is a Lewis acid-base reaction. It's not.
For the FeBr3.
This is our acid. It accepts electrons. This is our base. Donates
Why am
electrons.
I thinking this was ionic? Sorry.
I mean, it creates an ion.
It does? Okay.
Another reminder, I'm going to show these for this reaction as individual steps. For chlorination, I'll show it as a full sequence. You guys are welcome to copy it and repeat it on your homework and exams, whichever way you find more meaningful to you. If anything, I'd like to call this step activation of the electrophile. This group right here is my activated electrophile. Okay, what do I mean by activated electrophile? Br2 is the electrophile. It will accept electrons from the ring. FeBr3 is a catalyst. It makes the electrophile a better electrophile. So this is now a much better electrophile than Br2 is alone. So I like to call that my activated electrophile. I'd like you guys to recognize what I've done with my aromatic ring from the end of step 1 to this step. What do you see?
No change. It's drawn out with the double bond.
Yeah. What did you say, Rob?
No change.
No change. True. Other than how I represented the pi electrons. Here's a word of advice. Don't draw the circle. Because if you get into a habit of drawing the circle, but then you need to show the reactivity of the pi electrons, you can't show that reactivity from the circle. So then you got to go in and erase it and draw the pi electrons. I will take points off if you try to show this reaction from the circle. It just doesn't indicate anything meaningful. Which of these bromines is best attacked by the ring?
Positive.
Your first instinct is to say the bromine with the positive charge. What does that bromine want? The positive charge tells you that bromine wants electrons. So have the ring give that bromine electrons. And create a third bond to bromine? 2 bonds to bromine is rare enough. 3 bonds to bromine would be catastrophic. What if we gave it electrons back by taking it from the other Br? So I like to refer to this as a terminal Br. You can see that it is the furthest away from the iron, and so it's kind of sticking out there like a branch. This is the easiest Br for the aromatic ring to attack. By attacking that terminal Br, you break the bond, and you give this bromine back its electrons, neutralizes its charge. So first I'm just going to draw my ring, and then I'm actually going to draw FeBr4 minus. That's an intermediate of the catalyst. Now, 2 pi bonds are unchanging. Two pi bonds stay unchanged. 1 pi bond is lost by 1 carbon, used by the other carbon. So this gives me, well, does it matter which carbon uses the electrons and which one loses? Not in this structure. The regiochemistry is identical. It's a perfectly symmetric molecule. So this gives me Br and H on 1 carbon, and just H with a positive charge on the other carbon. Can you guys tell me so far, are all of my charges balanced? Yeah. Net neutral, net neutral, net neutral. That's important. Charges are a big part of predicting a plausible mechanism. So when I go in and grade yours, I'll be looking for, is it plausible or not? Am I done with this step? No. A plausible mechanism should show all major resonance forms. And this cation is conjugated with the alkene. So I need to show my positive charge being delocalized. Which means I can put it from being adjacent to the bromine to being opposite the bromine. And then I have one last resonance form where it's adjacent to the bromine again. All the while, I've got that FeBr4 minus. I'm going to call this step formation of the sigma complex. I didn't come up with that name, sigma complex. It's a term that you'll find in your textbooks. I'm not sure who picked it or why, but that sigma complex is this set of resonance forms. I suppose it's because you start with an aromatic ring, which has a lot of pi character, important pi character, and now you've kind of broken that aromaticity because you've got this sp3 hybridized carbon, and so they call it the sigma complex.
And you wanted to do the whole resonance every time?
And I'll give you a hint. Once we start putting other groups on, 3 is the least number of resonance forms. But you can have upwards of 4, 5, 6, 7 resonance forms. So resonance is a big part of this chapter. Now, I do want to say something else about drawing a mechanism. I like to put my resonance forms in these big brackets. Kind of points out that these are not separate steps. Notice that I have them related to each other by resonance arrows, not reaction arrows. That's another point that I look for when I'm grading, is that you are relating the structures with the correct arrows. The other thing that I want to point out, so I won't take points off for these brackets. You don't have to include them. It just helps remind me, this is not a different structure. This is one compound. The other thing I want to say, though, is no doubling up on these resonance forms. And what do I mean by that? There will be some resonance forms. You guys agree that all resonance forms exist at the same time because none of those forms actually exist. So you can draw one resonance form to another resonance form at will. You don't have to draw them sequentially. I could have drawn this one, and then with 2 arrows, I could have immediately gone down to this one. Then I could have drawn 1 arrow back, and I could have gotten back to this one. What I don't want to see is for you to have this resonance form come down to form these resonance forms, and then also take this resonance form to the next step of the reaction. That's called doubling up. You've used this to show resonance and to show the next step of the reaction. Or, for instance, I don't want you to show this resonance form being used to form this and this resonance form. You've doubled up one resonance form being shown creating 2 other resonance forms. I want each resonance form to only be related to one other structure going forward, not to be related to multiple different paths. Why? Because you're predicting a plausible electron arrow pushing mechanism. Any of these resonance forms can be used to go to the next step because they are all equal to each other, more or less. They all exist at the same time. So I don't want you doubling up because each one can be useful. All right, this is our 3rd and final step. This is the elimination step. I think the other thing that I could have called this, instead of formation of the sigma complex, I could have just called this addition. Correct? Consumed a pi bond. So that's an addition step. This is an elimination step, but I can also call it reformation of the aromatic ring. And that's the primary objective here. Now I'm going to take the last resonance form that I had, not because it's any different than the others, but just because if I were to string this together, this would be the one I had used last. I'm going to bring back FeBr4, but I'm actually going to highlight one of the FeBr bonds, because we said one of our byproducts in this reaction is HBr. Br takes the electrons back from iron, bonds to the hydrogen. And the CH bond, which is owned by carbon, carbon is more electronegative, the CH bond goes through elimination, forms a pi bond. I reform my aromatic ring, and I have a byproduct of HBr. Now, tomorrow, we're going to look at chlorination, alkylation, and acylation mechanisms. And then we'll start looking at what happens with polysubstituted benzene rings. What happens when I start having these groups on, and then I run a reaction? How do those groups impact the reactivity? And then Thursday, we'll look at NAS mechanisms and reactions, kind of the same idea of reactivity with different groups, and we'll apply it towards some multi-step synthesis. In the meantime, I really do believe that you can start predicting the chlorination reaction. And with a little outside resource like your textbook or the internet, I would not be surprised if you could get a start on the alkylation and acylation before tomorrow, but that's where we'll pick up.
That's right. The book is half of what you put in there.
All right. I'm sorry for taking you guys over. Thank you for your time, and I'll see you tomorrow.